So now in this video, we're going to start talking about magnetic fields. Electrons are just charged particles in motion, and we know that charged particles in motion can create magnetic fields. So it shouldn't be too much of a surprise that a magnetic field can change the way that the hydrogen atom behaves. Before diving too deep into the quantum mechanical parts of this, let's start by recapping the magnetic moment that's produced by a particle in motion. So what we have over here is we imagine we have a charged particle Q that has charge Q, and it is rotating in this ring with a particular velocity, and the ring has a radius r. Okay, so you have this charged particle moving around. The motion of the charged particle creates a magnetic field out of this plane, and the magnitude of that magnetic field will be related to, and the magnitude of that magnetic field, which we call the magnetic moment. I'm going to start by writing it like this, and the notation will make more sense in just a moment. Okay, and this is equal to Q times R times V divided by 2, where again this Q is the charge, R is the radius of this motion, V is the velocity at which the particle is moving, and all this is divided by 2. Or looking ahead, because we know we're going to be trying to put this into a quantum mechanical framework, we can write this instead using the momentum. Okay, so this tells you the magnitude of the magnetic moment produced by a particle rotating in a ring with a given charge, velocity, and radius. So for example, if you believed the Bohr model of the hydrogen atom, then this would tell you everything you need to know to figure out the magnetic moments of the different orbits in the Bohr model. But we know the Bohr model is not correct, and so we need to look at something a little bit more complicated. And so if we start by looking at what this magnetic moment would look like if we don't quite have a circular orbit, if instead we have something more complicated, then the magnetic moment we need to think about as a vector now. And this vector is equal to Q over 2 times R cross V, where R is the vector that connects the origin to the particle, and V is the vector of the velocity of the particle. And this is a cross product here, right? So this produces another vector, and so the magnetic moment is a vector. Or again, we can write this using the momentum as Q over 2m R cross P, using the fact that the velocity is just the momentum divided by the mass. Now you might recognize this bit here. This R cross P is actually just the vector notation way of writing the angular momentum. Right, so put another way, this becomes Q over 2m times the angular momentum vector. Right, so this is the classical angular momentum vector, which is just equal to R cross P. So if we take this and we plug in the values for the electron, right? So then that means that the m sub l vector, so the magnetic moment vector for the electron, is equal to minus e over 2m sub e times the angular momentum vector, right? So where minus e is the charge on the particle, and then m sub e is the mass of the electron. So this is a more or less classical expression for the magnetic moment of an electron in motion. Now to figure out what the energy of this particle would be inside of in a magnetic field, right, it's going to be an interaction between this produced magnetic moment and the magnetic field. And the way this will look is like this. So we have this produces a new potential if you turn on a magnetic field. And this will be equal to minus ml vector dot product into B vector. So the m sub l again is the magnetic moment that's produced by this electron in motion, and the B vector is a vector of the magnetic fields in different directions. Okay, now without losing any generality, we can choose the magnetic field to be aligned only in the z-axis. And if we do that, then this just turns into minus mlz, so this is the magnetic moment in the z direction, times bz, which would be the magnetic field in the z direction. And now if we plug in our values for mlz from above, E times bz divided by 2m sub e times lz. Okay, so this is the angular momentum around the z-axis. This is the magnetic fields in the z-axis. And then these are some constants that are associated up front. Okay, so this is a classical description of this magnetic field. It'd be really simple to take this classical version and turn it into a quantum one by taking this L and then just adding a hat to it. Now what we have is a potential energy, or an energy term that we can add to the Hamiltonian that incorporates the effect of turning on a magnetic field in the z direction. And in particular, it depends on the angular momentum operator around the z-axis. So if we want to know what happens to the energies of an electron after we turn on a magnetic field, what we do is we start by rewriting the Hamiltonian. We're going to write, we have a Hamiltonian H. We're going to say that this Hamiltonian H includes what I'm calling H0, which is quote unquote the normal hydrogen atom Hamiltonian. Or also referred to as the electric Hamiltonian, because it only includes electric terms. And then we're going to add to this the term that we just derived for the energy in the magnetic field, which will give us E times Bz divided by 2me times Lz hat. And so this second term we refer to as this is sort of a perturbation, meaning that we're disturbing the system in some way by a magnetic field. Now I'm going to rewrite this in a slightly different way. So H naught is the same. We're going to define a new constant called beta B, which is known as the Bohr magneton. So the Bohr magneton is defined like this. It's elementary charge times h bar divided by 2 times the mass of the electron. And so this is called the Bohr magneton. You can think of this as the elementary unit of a magnetic field, just like E is kind of the elementary unit of an electric field. You'll see in a moment why we give it a somewhat strange definition here. Okay, so recap, where are we? So this now is the Hamiltonian that corresponds to a hydrogen atom. So this H naught contains just the parts of the bare hydrogen atom, and then sitting in a magnetic field. And so the second term contains all of the parts that tell us how this is going to interact with a magnetic field. And this magnetic field term ends up depending only on the angular momentum around the z-axis, the way we've built this. Remember, we chose our eigenstates of the normal Hamiltonian to also be eigenstates of Lz and of L squared. And so because our eigenstates are already eigenfunctions also of this operator, of Lz, it means that the eigenfunctions actually don't change at all when you turn on a magnetic field, but the energies will. And so I'll go through a quick example to show why that works the way it is. Okay, so let's take our perturbed Hamiltonian. We're going to apply it onto the NL m sub L eigenstate of the hydrogen atom. So this is now Brockett notation, but it means the same thing as applying it onto psi n L m sub L. So let's use our definition of the Hamiltonian. This would be H naught times n L m sub L plus E times Bz over 2me Lz hat times n L m sub L. Okay, now by construction, these are eigenstates of H naught, and so we know what the energies coming off of these ought to be, and these will just be En times n L m sub L. And then the second one, again, these functions are also eigenstates of Lz with eigenvalue h bar times m sub L. So we plug these in now, and what we get is E bz over 2me times m sub L times h bar on nl m sub L. Or in other words, this is equal to En plus beta b Bohr magneton times m sub L times the original function. Okay, so what this tells you is that your energies just got this extra term in it, which is proportional to m sub L and is proportional to the magnetic field. So what this means is that without a magnetic field, the energies of all of these states only depend on the principal quantum number n. There's no L or m sub L dependence in the energy, it just depends on n. But when you turn on a magnetic field, all of a sudden the energy changes depending on the different values of m sub L. Okay, so let's think about what this implies. So we know already that if we have no magnetic field, there are three 2p eigenfunctions that all have the same energy. But now if we turn on a magnetic field, the three 2p functions have m sub L values of +1, 0, and -1. And so if we turn on a magnetic field, the stronger we make it, there's this extra term in the energy that's proportional to this m sub L. And because they all have different values now, it means that as the field gets stronger, you'll have one state that gets higher in energy, that has the m sub L +1, one that gets lower with m sub L -1, and then one that stays the same, and this is the one with m sub L is equal to 0. Okay, so without a magnetic field, all of these have the same energy, and so it means that you would expect to see just one energy when you have a look at a transition from the 2p to the 1s. And now you turn on a magnetic field, these three different p orbitals all split in energy ever so slightly, and now what you'd observe is three distinct lines, one from each of these split p levels. And so now you'd see three separated lines, and the separation between these lines is proportional to the magnitude of the applied magnetic field. And so now in this case, you'd expect to see three distinct lines. Okay, so this is the basic outline of magnetic interactions in the hydrogen atom. In the next video, we will talk about the fact that when you observe this spectrum, you in fact don't even see 3 lines, you in fact see 10 lines. And even worse, this without a magnetic field, where we should be seeing just one line from 2p to 1s, we in fact see a doublet. Okay, so that means that there is a whole nother interaction happening in the hydrogen atom that we have not talked about that is leading to extra lines being observed. And that will turn out to be the electron spin, which we will talk about in the next video.